Greetings of the day. I Asha K, Assistant Professor, Department of Electronics and Communication Engineering, Sai Vidya Institute of Technology, Bangalore, going to present in today's class Digital Signal Processor Algorithms and Architecture for the 7th semester elective course. In today's class, we will learn about the Module 5 Speech Processing System concepts. We have here digital model for the production of speech signal, autocorrelation and autocorrelation computation, and also implementation of the concept on the DSP processor. A speech processing system basically consists of nasal tract, vocal cords, and also our lungs involved here. The purpose of speech processing basically is for the analysis, transmission, or reception, as in the case of radio, TV, phone, denoising, compression, etc. Everywhere the speech is very important. Human can understand with another person with the help of a speech. Processing of this speech is required. There are various applications involved for the speech processing, which includes identification and verification of speakers, speech synthesis, voice to text conversion, and vice versa, and so on. A speech processing system basically consists of vocoders. These are called as voice coding and decoding circuits. A general problem which occurs in the speech processing system is pitch period estimation, on what pitch the person is talking and what is the fundamental frequency of that particular speech. It is very important. Here we learn the pitch period estimation using the autocorrelation technique. A speech production mechanism is shown in this particular figure. It basically consists of muscle force, lungs, trachea bronchi, vocal cords. It also consists of vocal tract and a mouth. And along with that, we also have here nostril, which is involved in the speech production, and a nasal tract, which is involved in the speech production. And we have a palate membrane, which is called as the velum, and it is also involved in the speech production mechanism. Velum is nothing but a soft pellet. Whenever we are swallowing or sucking the food, it closes the nose track. It keeps the separation between the mouth and nose. This is the speech production mechanism. Whenever we wanted to talk the alphabet such as a, ba, ka, or ma, so some of the alphabets requires the phenomenon of nasal tract also, whereas nostril is also involved here along with the nostril tract. In Kannada, we call it as Anunasika, Swara, and Vyanjana, all those things. In English, we call it as consonants and vowels generation. Generation of speech is very important. In this generation of speech mechanism, the vocal tract has a vocal cord at one end. So we have a vocal cord at one end. So this is the vocal cord that we are having. The shape of the vocal tract that we are having here depends on the position of the lips that we are having, jaws that we are having, tongue, and the velum. And here this decides the sound that is produced, what kind of that sound that we are producing. And there is another tract, nasal tract, present in the speech production mechanism. The movement of the velum connects or disconnects the nasal tract. The overall noise depends on the sound, depends on the vocal tract and the nasal tract. The two types of the speech are voiced sound and the unvoiced sound. So we are going to get both voiced sound as well as the unvoiced sound here. The vocal tract is excited with quasi-periodic pulses of air pressure caused by the vibration of the vocal cords resulting in the voiced sound. And here, unvoiced sound is produced by forcing air through the construction formed somewhere in the vocal tract and creating turbulence that produces the source of noise to excite the vocal tract. Whenever we are crying or whenever we are laughing, different sounds or speech information, whenever we are happy or whenever we are sad, different kinds of different types of speech or different kinds of words will come out of our speech production mechanism. So this is the human speech production mechanism principle. A simplified speech production model is shown in figure here. The figure 2 is the speech production model. In the speech production model, we have a pulse train generator that generates the voiced information. Sometimes we also have a surrounding noise generated. These are called as the unvoiced signals. And when it is combined and when it is passed through the vocal tract, we are going to get the speech. That speech is a combination of both pulse train of generation with the noise signal. The pulse train generator generates the pulse train, thus it represents the voiced speech signal. Noise generator represents the unvoiced speech signal. Vocal tract system is supplied either with the periodic pulse train or noise. The final output is synthesized as the speech signal. Here, the fundamental frequency of the speech differs from one person to person. Hence, the sound of the speech also differs from one person to another person. A few persons are like softly spoken. Few persons are like their voice will be very like high pitch. So it depends. Speech is a non-stationary signal. However, it can be considered to be relatively stationary in the interval of 20 milliseconds. The fundamental frequency of speech can be determined by autocorrelation method. So this is the simplified speech production model shown in the figure 2. Now we'll discuss about the block diagram of pitch period estimation using the autocorrelation function. A three-level clipping scheme is involved here to measure the fundamental frequency of the speech signal. The block diagram is shown here for the clipping autocorrelation pitch detector. It basically consists of an S of T signal. S of T is a analog signal which is continuous in nature. It is a speech signal. It is passed through the low pass filter, which is an analog filter, and 0 to 900 Hz bandwidth. Then analog to digital converter with a sampling rate of 10 kHz is used here. Then we are going to get the digital signal which is called as S of n. Here this S of n is divided into sections. Each section is having 30 milliseconds of duration. Such 300 samples are considered for the pitch period estimation. These 300 samples are selected at 10 milliseconds interval, thus the segment overlaps by 20 milliseconds. So here we have to find the absolute peak level over the first 10 milliseconds, which is called as IPK1, and to find the absolute peak level over the last 10 milliseconds, we call it as IPK2. Similarly, in this case, the average absolute magnitude is computed with the 100 samples of information. So this 100 samples of information, in this case, it consists of peak signal level in each segment are compared to the threshold determined by measuring the 50 milliseconds of background noise. After measuring with the threshold of 50 milliseconds of background noise, with the help of a compare peak signal with the threshold, that is silence threshold, and compute the silence threshold level, we are going to find the whether the speech signal that what we are getting is a silence signal or whether it is a speech signal. Once we come to know that it is not a silence signal, then we are going to process with the help of a 3-level center clipping concept. So once I came to know that the voice data that I am having is not a silence, then what we are going to do here is with the help of IPK1 and IPK2, we are going to set the clipping level. The clipping level is called as CL, that is equal to K into minimum of IPK1 comma IPK2. That will be subtracted with the function K. And after obtaining the clipping level, that is connected to the center clipper. In center clipper, we will be having the 3 levels, that is 0, 1 and +1. Based upon this, whether the data that we are having, it is like it is equal or it is matching or it is not exactly connected, is decided based upon the center clipper with infinite peak clipper. And after getting the data, that is autocorrelation computation is performed using the autocorrelation equation. Once we get the output of the autocorrelation, that is we are going to find the position value of the autocorrelation peak. When I have a two signals, the autocorrelation of say that particular signal, auto means self, relating the same signal, same speech signal with the same signal itself. After relating, we are going to get the peak of the signal at zero lag. After getting the peak of the signal at zero lag, find the position and the value of the autocorrelation peak. Then what we are going to do here it is, we are going to compare this peak value with the U or V threshold value. After comparing with the, that is U stands for unvoiced data or V stands for voiced data. If the peak value is like compared, and after comparing, if it is below the threshold means we call it as an unvoiced signal. If it is above the threshold means we call it as the voiced data or the voiced period. So this particular diagram is explaining the uh, clipping autocorrelation pitch detector and how the pitch is detected for the voiced period. So this data will consist of the voiced period information, whereas this data after comparison will consist of the unvoiced information. Autocorrelation computation. The autocorrelation of an y of n is computed with which will be having three different levels, 0, +1 or -1. Here if we are having these three different levels, the autocorrelation of a sequence y of n is given by Rn of k is equal to summation m ranging from 0 to n minus 1 minus k y of n plus m into y of n plus m plus k. Here, the correlation of the signal y of n plus m with the y of n plus m plus k results in three different levels. If this is equal to 0, then both the sequence y of n plus m is equal to 0 or y of n plus m plus k is equal to 0. If both are equal, that is y of n plus m is equal to y of n plus m plus k, then the output is +1. If y of n plus m is not equal to y of n plus m plus k, the output of this is -1. Three different levels will be like obtained. The three different levels clipping output is shown here. This is for the +1, this is for the -1, and in between if it is not above or if it is not below we'll be having the 0, and this is the clipping level that we like calculated using the IPK1 and IPK2 in the previous diagram. Here, the speech signal S of t is filtered to retain the frequencies up to 900 Hz. A low pass filter is used for that particular purpose. The sampled, it is using the analog to digital converter to get the digital data yes often. The speech signal is an analog signal. It is in the continuous in nature. It is converted to digital using the analog to digital converter. The sampled signal is processed by obtaining or dividing it into samples of 30 milliseconds duration as discussed in the previous block diagram. And here the with the 20 milliseconds of overlapping of the window is chosen in this case. The average of absolute magnitudes is compared with the 100 sample rectangular window to obtain whether the speech signal that we are connecting as an input is silence, or it is a voice data, or it is an unvoiced data. So all the three outputs, like any one of the output we may get out of it, and after getting the voiced data or voiced information, we are going to find the pitch period of that particular voice. That is also called as the fundamental period of that particular voice signal. So now we'll discuss about the next topic, that is implementation on the TMS320C54XX processor. That is the concept of speech signal or speech processing implementation on this DSP processor. The speech samples were recorded using the voice recorder software in Windows 98. The signal was sampled at 16 kHz in 16-bit mono format. After getting this, the autocorrelation module is the most computation intensive section of the pitch period detection. For this reason, the DSP was used to compute a 400-point autocorrelation for a 480 sample segment in this TMS 320C54XX processor. For the sampling frequency of 16 kHz, 30 seconds of speech corresponding to 480 samples, and it may take about 17,200 clock cycles of time duration 0.17 milliseconds for TMS320C5402 processor, which is running at the frequency 100 MHz. The timing can be improved by using lower sampling rate, thereby reducing the section size, reduction of the window size for computation of the autocorrelation. Now we'll just observe the implementation of the speech processing concept on the TMS320C54XX processor. First we will observe the autocorrelation output for a voiced speech segment. This is the diagram that we are having. Autocorrelation output for a voiced speech segment. This is the pattern. Whereas if you just observe autocorrelation output for an unvoiced speech segment, the diagram we are going to get like this. So we can say that here there is a peak, but if you just observe here at the 0th position we have the peak, but gradually the voice is decreasing. So unvoiced speech, the amplitude of the autocorrelated sequence is decreasing here. So this is the difference between the autocorrelation of the voiced speech segment and autocorrelation of the unvoiced speech segment. So now at the end of the class, the outcome of this particular class is what we have learned. We have learned the speech production system, that is digital model for the production of the speech signal. We have also learned the computation of autocorrelation and also three-level clipping mechanism, a block diagram representation of the complete speech processing system with the pitch period estimation using autocorrelation, and also at last we have learned implementation on the DSP processor. To prepare the content in this particular presentation, the textbook referred is this and the reference books referred are the following. Thank you all.